Hello, good afternoon. For those of you in Central Time, I'm Daniel Lichtblau. I will be giving this talk, What's New in Matrix Algebra Functionality. In short time, I can't cover the new functionality in 14.3 that we released in 14.3. I won't have enough time to go over what's coming out in the next release. So it's going to be a bit of a whirlwind. So buckle your seat belts and keep your hands in the car at all times. Okay, functions we introduced in 14.3 that are matrix algebra and closely related. You'll notice it's a sort of a wide range. We're filling in gaps that we've just perceived as missing over the years. Some of these, the polynomial Hermite-Smith decompositions, have integer analogs, so they live really more in Euclidean rings than in linear algebra over a field, those of you that are familiar with the underlying algebra. Um, we also added these reduce versions, Hermite reduce, Smith reduce, and same with polynomial Hermite and Smith, which I seem to have missed one of here. Those are short forms that skip creating conversion matrices, and sometimes people want those. We've had them requested, and they can be faster to compute than the full decompositions. And we are adding more of those in the next release, as you'll see in a moment. Um, Other than that, there's companion and Jordan matrices are kind of obvious things we were missing, and they were easy to add. Uh, a bunch of these matrix minimal polynomial and the polynomial Hermite-Smith decompositions came out of the function repository, and we had decided it was time to really bring them to system functions. Frobenius decomposition we had not had, and that's sort of like the Jordan decomposition, but it doesn't involve creating these horrendous root objecty things, so you get much more concise results and sometimes more usable. Uh, okay, so that was a quick recap of the version 14.3 new functionality. And I believe I made slides available or the talk available or both where these were introduced. So for anybody who wants to review them, that material should be available from the conference site. Assuming I got them in there correctly. Okay, so in version 15, again, many of these were in the function repository first. As I said, we've added some of these reduce shortcuts to give the normal, what are called the normal forms, um, rather than the full decompositions. We don't call this Jordan normal form or Frobenius normal form simply because the word normal in the Wolfram language generally has a very different meaning. So we went with reduce. And we're adding some decompositions, the polar and ranked and LDL, Bunch-Kaufman, and Popov decomposition. I'm going to talk about a lot of these individually, so I won't really go into any detail on this page. And I should add, these are currently provisional. I believe most, if not all, have been improved for release, but there may yet be changes as the design reviews pick up again prior to release. There might be name changes. Some might be added, some might be held back for a later date as redesign happens. So, this is tentative, although I'm hopeful it will all come to fruition. Um, and for some reason, my next cell button doesn't want to. Okay, so we'll do it that way. So the reduce functions, Jordan and Frobenius reduce. Uh, as I say, often one doesn't need a conversion matrix. The Jordan decomposition gives what's called a similarity matrix as well as the Jordan normal form. The Frobenius decomposition gives a multiplier matrix also, and sometimes these are expensive to compute, above and beyond computing the normal forms. So here's the Jordan reduction of an integer matrix. It's a very simple one. It has a repeated eigenvalue and it has non-trivial Jordan blocks, and it's the same as what we get from the Jordan decomposition second element. Just to clarify what we mean. The reduction gives the second part of the decomposition in this and many other cases. Usually the first part is the conversion matrix. Frobenius normal form, Frobenius reduce, same story. You get this. This is the Frobenius normal form for this particular matrix. And if I had, I'm not here, I could have shown that it's the same as what one gets from the second element of Frobenius decomposition. Okay. Oh, okay. So once again, my arrow button doesn't want to work for me. Okay, rank decomposition. This is actually similar to the range space, but I think a bit more useful. Range space was a function we introduced in 14.3. If you have a matrix dimensions m by n, but it has relatively low rank R, what you get is a pair of matrices. This is not a unique decomposition, but one is m by r and the other is r by n, and their product gives you the original matrix back. And as I say, if the rank is really a lot lower, and this sometimes happens, you deal with, in some places in the world of linear algebra, you deal with low rank matrices. And sometimes it can be very, you can save a lot of space, among other things, by rewriting as such a product. And here we have a 3 by 3 of rank 2. The rank decomposition has a 3 by 2 and a 2 by 3. And yeah. And because it's most commonly, we think, used in the world of approximate linear algebra, where you have machine real numbers for your matrix elements, say, you might want a tolerance option because the rank is a sort of how do I say it, an approximate measure, or I shouldn't say approximate. It depends on non-zero singular values, and you can have singular values that are small, but that don't quite evaluate to zero, and you use a tolerance to make them into zeros, and etc. Okay, so on to the next. The LDL decomposition. This is like the Cholesky decomposition, and it has been requested from time to time. It's where you have an Hermitian matrix that is not positive definite necessarily. It can be indefinite, it can be semi-definite, doesn't matter. And you decompose it like the Cholesky, which does require positive definiteness, except you now, instead of decomposing as L times L transpose, you have a diagonal matrix in the middle. So the Cholesky decomposition would be a special case where that diagonal matrix is just the identity matrix. And so here's a quick example. I just create and we return the lower part and the diagonal because the upper part is just the transpose of the lower part. So we don't need to show that. And here's a quick example. And just to show, this has negative eigenvalues, this input matrix. So it is not positive definite. It's not even indefinite. I'm sorry, it's not even semi-definite. It is indefinite. It has both positive and negative eigenvalues. And so there is no Cholesky decomposition, but there is an LDL decomposition. Okay, now a drawback to the LDL decomposition is that you're not allowed to pivot. as best I understand, or at least I don't know how to do it with pivoting. As a result, if in the process of doing row reductions of the sort that are done for the LDL decomposition, if in that process you were to encounter a pivot that's zero, a an element in the pivot position that is zero, you'd be, the technical term is dead in the water. And so you would not be able to actually do that decomposition. The Bunch-Kaufman decomposition generalizes LDL, and it has two nice attributes to it. One is it allows for pivoting, and the other is that it often gives a result that is in some sense numerically more stable, meaning it's easier to use that result, say, for a linear solver, for a Hermitian matrix. It's easier to use that in a way that keeps the conditioning of the result reasonable. It doesn't blow up the condition number the way an LDL decomposition might do. So that's kind of nice, because I mean, among other problems with the LDL, even when you can pivot, you might have a value that's very small that you would prefer. I'm sorry, even if when you have a viable element non-zero in the pivot position, you might prefer to pivot it away. Bunch-Kaufman allows you to do that. The difference, however, the minor drawback, is that now your diagonal is actually block diagonal, because you may have 2 by 2 blocks. This will happen when you actually pivot. And so we get, here's again a quick example where we now get a permutation as well as the lower triangular matrix and the block diagonal matrix. We get this permutation, and the identity that they satisfy is that, oh gosh, I can't believe I did this. I'm sorry, I apologize. I did not set up this slide correctly. So, or did I? I'm just using the terminology from LDL. I should be using a different, slightly different, but yeah, D is block diagonal. That's the only difference. And we now use the permutation on our matrix, original matrix, on both sides to get an identity. Or we could reverse the permutations, put them all on this side, and would be equal to P transpose dot L dot D dot L transpose dot P. Yeah. Anyway, we typically worded this way. Okay. What else did, in both cases, I guess I should have said this, for LDL and for Bunch-Kaufman, the L matrix has ones on the main diagonal. So in some sense, it's really strictly lower triangular plus an identity matrix. And that's convenient for like using these in a chain to do a linear solve type operation, but to do it in a way that's numerically stable. Okay, on to the next. Popov decomposition. This is like the polynomial Smith and Hermite decompositions. It is, in other words, it lives in the world of Euclidean ring of univariate polynomials. And so it is the analog in that polynomial domain, the analog of lattice reduction. And so here what you get, you're trying to reduce polynomial degrees while generating a polynomial lattice that is the same as your original set of polynomials. Think of the row vectors as, you know, the set of polynomials that generates a lattice-like thing in polynomial world. And so, as with Smith and polynomial Smith and Hermite, your conversion matrix is always what's called unimodular, meaning it is invertible in the polynomial ring. It doesn't involve any, the determinant has no polynomial in the denominator, has no polynomial, I'm sorry, the determinant is a constant, is what I meant to say, so that if you were to invert it using Kramer's rule, you would have a constant in the denominator rather than a polynomial. So no rational arithmetic is ever needed, is the nice thing. You're, in terms of rational functions, you're just working with polynomials. Okay, and now to talk a little bit about upgrades. Small one, QR decomposition now takes a full specification, so we can do what's called a full QR decomposition instead of limiting the size of the what would be the orthogonal square matrix. We by default chop it off, and so that it's not, it's just got orthonormal vectors in it, but it's not actually an orthogonal matrix because it's no longer square. In the full case, we make it a square orthogonal matrix, and for some purposes that's useful. For some, it's not. So it varies. The big improvement, matrix function for exact integer or rational number matrices is now much more efficient, and it gives a much smaller result. And I show a quick example of that here. Previously, this gave a huge result. So a fraction of, less than half a second versus 67 or so seconds, a result that takes almost 10 seconds just to get the leaf count is now immediate, and it's, under 10,000. It's orders of magnitude smaller, and it evaluates numerically using n immediately, whereas before it took, 2.5+ minutes. That's a huge improvement. Much as I'd like to take the credit, this is actually new due to the literature. It's Arturas Akis and Adelphus Dargis. Arturas sometimes posts on Mathematica Stack Exchange, I believe, and he had submitted this also to the function repository. I, there is a reference to this work, but it's only on arXiv. I don't think the actual article has been published yet. I don't know why. I think it's been approved, but not yet in the literature. Anyway, so it's a really nice development, and we're very happy to have used it. By the way, we were encouraged by the WFR function author to adapt it to become a system function, and we were more than happy to oblige. Go to the next slide. Okay. Yeah, new functionality. Not supposed to talk about this, but whatever. We extended the Arnoldi method for computing, say, just the largest or just the smallest eigenvalues, so that now you don't actually have to give a matrix. If you have this huge matrix, or if you can only generate dot products using some program, so it becomes a black box function, you no longer need to specify the matrix, but you do have to say what the dimension is that it lives in and how it operates. And I just give a quick and dirty example. Now, this is not a system function at this time, and I don't know. I think the hope is that we'll at least get it into the function repository shortly after the next release goes out. I can't put it there now because the code it uses isn't in any previous or existing release. So right now it's in the linear algebra context, and it's matrix-free eigenvalues, matrix-free eigensystem, and you specify the dimension, and you specify your black box function, which in this case is just, we actually do have the matrix at hand, and I'm just specifying the function as a take the dot product with whatever you're given for input, and that input will be a vector of the appropriate dimension, 30 in this case, and we can go ahead and compute those eigenvalues, the two smallest, because I think I said -2. Yes, I did. Okay, And if you compare to the default eigenvalues, which has its own code, but in some cases less efficient, particularly for very large matrices, and of course won't work at all if you don't know the matrix, you just have the function. So this is some nice new functionality that's been requested, and it's not yet a system function, and I don't know if it'll become one, but it will certainly be available. So I can wrap up. We're just past 20 minutes, I think. So we're introducing a lot of matrix algebra, linear algebra functionality. Um, yeah, okay. I can't resist a bunch of puns. So it's a bunch of functions and a bunch something function. And we also have put in a lot of upgrades under the hood. Um, I'm expecting that there will be more down the road, but I think versions 14.3 and what I assume will be 15.0 are the big ones for us in terms of introducing new linear algebra functionality. And acknowledgments, I do thank Devendra Kapadia, Roger Germanson. Um, they did a lot behind the scenes on the design specs for these functions. And they and Itai Segev have put a lot of time into documentation. I've also worked on the documentation, but they do some of the preliminary and then some of the fine tuning, a lot of fine tuning and examples, adding of applications examples gets done by these folks. And I thank Ying Yin because I would never have found all the headaches that she has found in terms of things breaking. You know, I fix one thing and don't realize that something else might be giving way, and kind of hoping that we have all this out of our system at this point, and that this will go into the next release with pretty painlessly at this point. Okay, so without further ado, I'll wrap it here, and I'll start checking the chat and Q&A to see if there's questions. I'll tackle them. Um, none so far. Um, okay. Well, if nothing else, maybe I've cured a few cases of insomnia. I don't know. Okay. Well, I will stay on this until we've got 7 more minutes, and I'll just hang out here. And if anybody, if questions come through, I'll happily. I do have one from Mads. What is my favorite decomposition matrix function? Well, okay. I think I have 2 right now. One came out in the last release. It's the Frobenius decomposition, because we should have had it for about the last 3 decades. And anytime it came up, I sort of put it off because I didn't know how to do it. And this time I finally basically was told, you know, we really need this. And it was part of the linear algebra project, which I was assigned to. So I downloaded notes of course notes and papers and put together a method. It's a bit of a I don't know, sledgehammer to walnut. I think it's not the most efficient. It does work. One of the things I am hoping to do going forward is to finally implement a slightly, to me, slightly more difficult, but I think more efficient method, and get that in place, and maybe even add a method option. And yeah, so I kind of did enjoy learning about how this actually works, and getting into the intricacies that I had put off for 30 years. And okay, and I'm not exaggerating about that 30 years. This first came up in the mid 90s, if not earlier. The other favorite I have is the pop-off decomposition. Um, and that's because I put together methods to do it that are just completely unconventional. I think I use a Grebner basis over a module with a modulus. Uh, in the case where the polynomial coefficients what's the word I'm looking for, are rationals. There may be more efficient code for when it's approximate numbers, but the pop-up decomposition in the inexact case of inexact coefficients, it's debatable how useful it might be. But yeah, that was interesting just for the methods that I managed to throw together. I don't know how efficient they'll hold up to being in practice, but I was reasonably happy with results I was getting. So that was nice. Where are the real slides from Itai? The answer is they are on my computer. Because this is new functionality and not fully approved, I do not yet have clearance to make these available. When Devendra or Roger tells me I can do that, I will try to do that through the conference site or in whatever way is deemed okay. Sheldon Axler comment. I think what the Mathematica is calling the rank decomposition is often called the column row factorization. I believe you are correct. And it might even be a better name in the sense that decompositions usually have some kind of canonical form to them, whereas the rank decomposition is not canonical. And in fact, for exact versus approximate numeric matrices, we use very different methods. And you'll get, for the same matrix, if you do the exact one, you get one result. If you do n of that, you'll get a very different looking result. The reason is clear enough. Under the hood, we're going to use row reduction in the exact case, and because that's unreliable for discovering rank, we're going to use the singular values decomposition for the approximate case. So yeah, the naming rank decomposition is perhaps not entirely correct, and there does seem to be at least one other accepted name. Not my call though. This is a design decision, and all I can say is I think it's implemented right. This also has a slightly funny history. I just implemented it because I knew it was similar to the range decomposition. So I basically cribbed my own code from that. And then Devendra pointed out to me that it was in the function repository already. I just didn't think to look. Because a lot of these I lifted from the function repository. I'm not ashamed to say I cribbed things shamelessly. Some I cribbed from myself, some I cribbed from other people. John Mangleton wrote a few. There were others. Um, but what I found when I looked at the one in the WFR was that the implementation was almost the same. I think it was John's, and it was almost the same as mine. So no real harm done. Okay. Oh, sorry. There's more response to Itai. We will make it's fine to make them available. Okay, I will find out right after this talk ends how I go about getting them um, onto the conference site, and yeah, we'll proceed from there. How are we on time? We have 1 minute and 15 seconds left. Is there a library like LAPACK? Yes. No, LAPACK is used heavily. And in fact, for the Bunch Kaufman, I first wrote a reference implementation because I knew that our internal code for it was going to be hard for me to figure out. And then after I had the reference implementation, I did figure out the internal stuff. And I was able to hook almost every numeric matrix into internal code. It had originally been written in a way that only took symmetric complex matrices rather than symmetric or Hermitian, the more important case. And I altered some of it, but I wasn't able to figure out how to do the complex Hermitian case for big num matrices. If ever I figure that out, I'll run that through it's LAPACK like code because it's big nums, it's not LAPACK. But right now that's using my reference implementation. Everything else for numeric matrices is using LAPACK or our big num equivalent under the hood. which makes it really much, fairly efficient. I'm out of time. Okay. I guess I either am, have been already, it was cut off, or will be. So I will stop here. Thank you all for attending. Thank you very much.